we have picked up the red hot industry for chemical engineers, petrochemicals. Okay, so in the very first lecture of petrochemicals, we saw the politics and economics behind the petrochemical industry. Then in the last lecture, we followed it up with primarily the petrochemicals from C1 and C2 chemicals. Okay, now before we get on, a small classification of petrochemicals. See, you can classify the petrochemicals in many ways, but one way is to do it in three categories: light petrochemicals, medium petrochemicals, heavy petrochemicals. Light petrochemicals means, see, this light, medium, heavy is not based on weight. It is based on the number of carbon atoms. For example, the light petrochemicals are bottled fuel and raw materials for other organic chemicals like methane, ethane, ethylene. These are all light petrochemicals, right? The next lightest fraction comprises petroleum and light naphtha. Their boiling point 80 to 190 degrees. The hydrocarbon, which fit roughly in this group, is known as light petrochemicals. Then come medium petrochemicals. Hydrocarbons with 6 to 12 carbon atoms are called gasoline. That is the blue chip, right, which are mainly used as automobile fuels. Octane with 8 carbon is particularly good automobile fuel. That's how the octane number came and is considered to be of high quality. Kerosene contains 12 to 15 carbon and is used in aviation fuels and also as solvent for heating and lighting. That is medium petrochemical. Heavy petrochemicals, the bigger ones, right? These can be maybe diesel oil, right? And what else? Heating oil, lubricating oil for engines and machinery. They contain carbon 15 to 18 with boiling point between 570 and 750 degree Fahrenheit. The heaviest fraction is called bitumen, which is used to surface roads or for waterproofing. You would have seen, in many old buildings, they put, this black bitumen on top as a waterproofing so that water will not seep into the building, right? So that is bitumen. And the black stuff you see on the road, where road making, that is also bitumen. Bitumen, of course, can be broken down into lighter hydrocarbons using cracking, right? So this is light, medium, and heavy. Then typically we study petrochemicals under these categories: C1 compound, C2, C3, C4, and aromatics. Right, of course, I think it is missing here. Aromatic, you should add benzene, toluene, xylene, BTX. That is the typical. They come like, one family together. Aromatic will be BTX, benzene, toluene, xylene. Please add it up. C1 is methane synthesis gas. Syngas could be carbon monoxide, hydrogen, right? C2, ethylene and acetylene. C3 is propylene. C4 is butane, butene. And aromatic, BTX, benzene, toluene, xylene. Already among C1, in the last lecture, we have seen methanol, especially the low pressure ICI process, formaldehyde, HCHO, chloromethane, a very important set of solvent, methyl chloride, methylene chloride, chloroform, and carbon tetrachloride. So this broadly covers the C1 chemicals which we have seen. And among the C2, we have seen ethylene, which is got by cracking. And in fact, if you see the flow sheet of ethylene, you will see that you are getting propylene also there itself along with ethylene. Then comes ethylene oxide, a very important chemical for manufacture of many more chemicals. Ethanolamine, huge solvent, right? And ethylene glycol, what is this gas? Another solvent. And vinyl chloride dictates the polyvinyl chloride polymerization industry ka major input. Vinyl chloride is also known as VCM, vinyl chloride monomer, and ethyl alcohol, right? Of course, main source of ethyl alcohol is by fermentation of sugar plant-based molasses, but petroleum industry can also be used to make ethyl alcohol. Nothing prevents it, right? And then these all we saw the tick one, and we had left out trichloroethylene, acetaldehyde, acetic acid, acetic anhydride, and vinyl acetate. We start with where we left, that is the C2 chemicals, trichloroethylene. Now, you see, I had also mentioned in the last lecture, carbon tetrachloride under pyrolysis gives you tetrachloroethylene, right? Carbon tetrachloride on pyrolysis gives you tetrachloroethylene, which is a what is used as a solvent, especially for the dry cleaning. Dry cleaning of clothes is done with tetrachloroethylene. And trichloroethylene is also a useful solvent, is used very widely, but trichloroethylene is not good in the dry cleaning part. So although trichloroethylene is giving a run for money to tetrachloroethylene, but when it comes to dry cleaning solvent, tetrachloroethylene still predominates. Of course, trichloroethylene is there for many other purposes. Trichloroethylene was prepared first in 1864 by Emil Fischer in experiments on reduction of hexachloroethane with hydrogen. This is the historic part. Commercial production of trichloroethylene began in Germany in 1920 and in the USA in 1925. Originally, it was acetylene-based process. It had two steps. Acetylene was chlorinated with a chloride catalyst to produce 1,1,2,2 tetrachloroethane, and then you can see 1,1 acetylene means C2H2, 2 carbon, right? So 2 chlorine go to 1 carbon and 2 chlorine to the second carbon. That is how tetrachloroethane is formed, and then this product was dehydrohalogenated to trichloroethylene, right? So first you go to tetrachloroethane and then dehydrohalogenate to trichloroethylene. Of course, this is the old acetylene-based route, but now more popular is the ethylene route. Trichloroethylene can be produced by using oxychlorination or non-catalytic chlorination of ethylene dichloride or other C2 chlorinated hydrocarbons. Another method involves using a catalytic hydrogenation of tetrachloroethylene, right? So by catalytic hydrogenation of tetrachloroethylene, I may be able to produce trichloroethylene, right? And trichloroethylene can also be produced by direct chlorination of ethylene in the absence of oxygen, giving a mixture of tetrachloroethane and pentachloroethane, right? The products are thermally cracked to produce a mixture of trichloroethylene, tetrachloroethylene, and hydrochloric acid. And this process was developed and is used in Japan. So you see that there's a whole variety of things, and reading through the description, you should be able to make a flow sheet yourself about how these things can be represented in a diagram, which I have not put here. I leave it to you. Okay. Then comes acetaldehyde, CH3CHO synthesis. Acetaldehyde, is a very valuable chemical that is widely used for production of other chemicals such as acetic acid, acetic anhydride, ethyl acetate, N-butanol, pyridine, vinyl acetate. For all these things, acetaldehyde is a starting point. Acetaldehyde can be produced by many processes such as partial oxidation of ethane, hydration of acetylene, right? Partial oxidation of ethane, hydration of acetylene, oxidation of ethylene, oxidative dehydrogenation of ethanol, dehydrogenation of ethanol. Right, so many options are available for acetaldehyde. Remember, alternate reaction paths is a very important aspect of process synthesis. You had already done in your first assignment for 2 chemicals, you looked at the various alternatives, right? So there are different routes depending upon the raw material available and the economics, the corresponding technology is chosen. Then the partial oxidation of ethane uses an expensive catalyst which requires high operating temperature. Hydration of acetylene uses a mercury complex as catalyst which is toxic. So that leaves us with oxidation of ethylene, which is also called the Wacker-Hess process, refers to the formation of polymerization and condensation products of acetaldehyde. Process pressure 50 atmospheres and temperature 50 to 100 degrees centigrade. They operate in the presence of aqueous liquid copper salt, copper chloride promoted by palladium. Therefore, it is costly and causes environmental problem. As compared with the above mentioned, we saw various alternatives for acetaldehyde. Production of acetaldehyde via ethanol dehydrogenation route appears highly attractive due to its cleaner technology. So we are not going into details of this ethanol and dehydrogenation of ethanol, right? So we straight go to the dehydrogenation route appears of ethanol, which is highly attractive due to its cleaner technology. The oxidative dehydrogenation of ethanol is another alternative route, which is quickly gaining widespread interest. Remember, we had mentioned oxidative dehydrogenation of ethanol and dehydrogenation of ethanol, right? So currently, these are the ones which are coming. The acetylene and the others have their inbuilt problem. So we look at the oxidative dehydrogenation. Acetaldehyde is produced by catalytic air oxidation, air, ethanol, right? Ethanol and air are the two raw material. They go to the reactor, right? And from the reactor, products are formed which are distilled, and our desired product acetaldehyde is removed, and the unwanted product contain, of course, the unconverted ethanol. So they are recycled back. Okay, so simple flow sheet, but if you elaborate this, many more details will come out, right? Catalyst used is a silver catalyst. The reaction is highly exothermic, and the reaction mixture containing mainly unconverted ethanol and acetaldehyde is absorbed in an ethanol water mixture, which is distilled to give acetaldehyde. Ethanol is recovered from the bottom, and the unconverted ethanol is recycled back to the reactor. So try to look up a more elaborate flow sheet for this oxidative dehydrogenation, because the other ethylene and acetylene processes, they have their problems, as we have discussed here. Okay, so now we move into the next chemical, acetic acid. Wow. Of course, acetic acid, something very familiar. What you use as vinegar is what is acetic acid, right? Apart from food application, acetic acid is that no sour taste, right? Acetic acid is mostly used for production of vinyl acetate and acetic anhydride, and also as a solvent. All labs shelves will usually have one bottle of acetic acid. It is a very common reagent which is present in all labs, right? Acetone, acetic acid, etc. Right? So the production of purified terephthalic acid, acetic acid, is a very important input. Until late in the 19th century, acetic acid was manufactured by age-old process of sugar fermentation to ethanol and subsequent oxidation of ethanol to acetic acid, which is still the major route for production of vinegar. Now this route is used only for production of vinegar, but commercial other purposes, we follow the acetaldehyde route. In 1916, the first industrial process for production of synthetic acetic acid was commercialized. This process was based on liquid phase oxidation of acetaldehyde. Acetaldehyde plus oxygen forms acetic acid, the exothermic reaction, right? Direct liquid phase oxidation of naphtha or N-butane. This is 1, 2, 3, 4 N-butane plus oxygen forms acetic acid. This is also exothermic reaction. Of course, I can use acetaldehyde or even naphtha or N-butane with oxygen can also give me acetic acid. This was one the preferred route, but because of low cost of these hydrocarbons, right? The mechanism for this reaction is also based on free radicals. It is not surprising that a major drawback of this process is that up to 50% of the feed goes to byproduct. All when there is a free radical, it is a free radical, right? It can jump from here and there and form a set of products which you may not be interested at all, like formic acid, higher acids, and aldehydes also end up forming. Many of which are very limited market, no takers. Furthermore, the process requires a very complex purification train, adding to the investment and operating cost. Now, only a very small portion of acetic acid is manufactured by this oxidation of naphtha or N-butane. That leaves the acetaldehyde as the in thing. Okay, acetic acid. So let's see what next. Now, the manufacture of acetic acid by Monsanto. Monsanto is another very major chemical global manufacturer. Monsanto, this methanol carbonylation, right? Using highly active and selective rhodium-based catalyst. Methanol plus carbon monoxide forms acetic acid, exothermic. Wow, catalyst is rhodium, right? And so you see the flow sheet here. I have methanol and carbon monoxide, 450 K, 30 bar, right? Continuously stirring, right? And my product go to a flash vessel where pressure is reduced and the liquid is recycled back, and the gaseous product go to a series of distillation columns which are separators. First column is light end column. The light gases are removed, and from the reactor also some light gases come. They go to off gas scrubber, right? This is for purification. Then I have part of what is this? The output of the light end column goes to a drying column, right? So in the dryer, and then the dried up products go to the final product column where I get acetic acid and top, propionic acid as bottom. The propionic acid is formed as a side reaction which cannot be avoided. Okay, so this is about the manufacture of acetic acid. Then comes acetic anhydride, CH3CO2O. Actually, these two should be a what do you call a subscript, right? CH3CO2 is a subscript, but typing, I think it has gone up, so make it a subscript, right? CH3CO, is the acetic, right? This is the anhydride, right? So you can easily write the structure of it. CH3CO, CH3CO, two of them is linked to two CH3CO is linked to an oxygen. Okay. Acetic anhydride, this is also known as, in short, AC2O. AC stands for this CH3CO is the short form of acetic. Acetic twice O, AC2O. Acetic anhydride is produced from glacial acetic acid, right? Acetic acid is the name for water-free anhydrous acetic acid. See, water-free anhydrous acetic acid is known as glacial acetic acid, right? So please keep it that you should know that when acetic acid has no water content, it is known as glacial acetic acid or anhydrous acetic acid. So acetic anhydride is formed via formation of ketene. This ketene is a very special organic compound, CH2 double bond, C double bond O, right? Imagine this carbon, this double bond with this carbon and double bond with this oxygen, right? So this organic, what do you call, functional group is known as ketene. Acetic acid is vaporized and fed together with a catalyst, ceric oxide, to a cracking furnace operating under vacuum where ketene is produced together with water at high temperature. Okay, the reaction mixture is rapidly cooled to avoid the reversing of the reaction, right? So rapid cooling so that reversible reaction is prevented. The condensed dilute acetic acid is separated and the gases pass through the two absorption towers in which they are scrubbed by acetic acid, acetic anhydride of various concentration. Glacial acetic acid is added to the second absorption tower because ketene is reacting with acetic acid to form acetic anhydride. Right? Is actually first a ketene form, and this ketene reacts with acetic acid to form acetic anhydride. So it is not acetic anhydride directly becoming, sorry, it's not acetic acid directly becoming acetic anhydride. So acetic anhydride first becomes a ketene, and ketene reacts with more acetic acid to form what we call acetic anhydride. So remember that acetic acid first forms ketene, ketene reacts with more acetic acid to form acetic anhydride. Right. So ketene is reacting with acetic acid to form acetic anhydride. In following washing towers, the gases are scrubbed before release to the atmosphere. In a distillation column, the crude acetic anhydride is distilled and recovered as bottom product. Top product is acetic acid, which is recycled to the process. That will depend upon the boiling point, right? Acetic, see, because some acetic acid is unconverted, so we have to separate and recycle it back. So you can typically expect that the product has got acetic anhydride and also acetic acid, which on separation will put acetic acid to the bottom of the column and acetic acid to acetic anhydride to the bottom of the column and acetic acid to the top of the column, which will be recycled. And acetic anhydride is the raw material for cellulose acetate, fibers, film, plastic, cellulose lacquer, aspirin, agricultural chemicals, fragrances, pharmaceuticals, and explosives. So you can see that acetic acid, acetic anhydride is a very important chemical in the petrochemical sequence. Now, simple flow sheet I am putting. We have acetic acid. It goes to reaction, catalyst, ferric oxide catalyst, a ketene is formed, and the ketene reacts with more acetic acid, and then you form a set of product, and then the acetic acid is recovered, and the dilute acid is brought back here, and the waste water is discarded, and from here it goes to distillation because still the product has acetic anhydride as well as some small quantities of acetic acid. So on distillation, I get acetic anhydride at the bottom. On top, I get acetic acid, which is recycled back. So this is the flow sheet of acetic anhydride. You see, by reading the reaction, you should be able to draw the flow sheet. That is how you develop. Otherwise, flow sheet cannot be mugged up. Then come the most important organic petrochemical, vinyl acetate monomer, VAM, VAM. VAM is a large-scale commodity chemical mostly used in manufacturing polyvinyl acetate, the basic ingredient in water-soluble acrylic paints. Paint is a big business in chemical industry, and vinyl acetate is there to come there into the paint making. Other applications are coating for textile and paper industries, laminated safety glass, right, packaging, automatic fuel tank, and acrylic fibers, right. Three main routes for vinyl acetate manufacturing are employed today. There are three routes we are first discussing. The first route is acetic acid and acetylene. Remember, by default, most acetylene processes have problem, right? Acetylene processes are the old one which have mostly got replaced. So that doesn't mean we don't know about them. So you have acetylene plus acetic acid forms acetic anhydride, exothermic reaction. The operating conditions are gas phase, 170 to 250, zinc AC2 catalyst is impregnated on charcoal. This is a catalyst, and Per pass acetylene conversion is 60 to 70% with selectivity of 93% acetylene and 99% acetic acid. High acetylene cost and safety problem. See, acetylene is quite an explosive one. You know, triple bond, double bond is ethylene, triple bond is acetylene. So the more unsaturation, the more reactive the compound is, and safety precautions, acetylene cylinders have to be handled very, very carefully. So the high cost of acetylene and safety problems make this process less competitive today. Then comes acetaldehyde and acetic anhydride. So remember, we are making vinyl acetate. This is one option which we have said that no, not okay. Second option, let's see, acetaldehyde and acetic anhydride. This process takes place in two stages. First, acetaldehyde and acetic anhydride form ethylene diacetate in liquid phase at 120 to 140 with ferric chloride as catalyst. So you have acetaldehyde and acetic anhydride, right? So acetaldehyde and acetic anhydride, they form this ethylene diacetate. And in the next step, this ethylene diacetate splits into vinyl acetate and acetic acid. Okay, so this process may rely completely on renewable raw materials. Wow. Then comes the third one. Acetic acid, ethylene and oxygen route dominate today. See, ethylene domination is obvious because cracking produces petroleum refining, cracking is there, and cracking produces ethylene. And most of the refineries, they don't do polymerization of olefins, so the ethylene is available for the chemical industry. So acetic acid, ethylene, and oxygen route dominate today. In the older technology, the reaction was conducted in liquid phase, 110 to 130 degree and 30 to 40 bar pressure in the presence of a redox catalyst, palladium chloride, copper chloride, but corrosion corrosion raised problem, right? And modern processes operate in gas phase, right, with the palladium-based catalyst. A highly undesired secondary reaction is the combustion of ethylene to carbon dioxide. So we can't prevent some side reaction comes into picture. But modern palladium AU, remember, aurum, gold, but don't forget the chemistry of school, right? Platinum, palladium, gold catalyst. The selectivity may reach 94% based on ethylene and 98 to 99% based on acetic acid. The removal of carbon dioxide, usually by a wash with hot potassium hydroxide solution, negatively affect the overall economics. Okay. Hess Celanese is a major chemical company. Bayer DuPont, they are the most, Hess Celanese, Bayer DuPont. These are the most widespread processes, the main difference being in the formulation of the catalyst. With respect to reaction engineering, a multi-tubular fixed bed reactor, FBR, a fixed bed reactor in short is FBR, is employed where the operational difficulty is mastering the occurrence of excessive temperature rise, hot spot. So remember, exothermic reaction. Recently, fluidized bed reactor technology has been developed with better productivity and 30% lower investment. These are reactor design ways by which new technologies are being dictated. Now, looking at a simple flow sheet, I put oxygen, ethylene, and acetic acid. This is my input to the reactor, and you know the catalyst there, right? And then it goes to a distillation from where I get my vinyl acetate. So this is a simple flow sheet, but on elaboration, you will get it like this. Wow. Ethylene, acetic acid, oxygen. So three inputs, right? Ethylene, acetic acid, oxygen, right? And the acetic acid is what is that? Vaporized, right? And then further heated and then put to the reactor. and some unreacted acetic acid is the recycle back that also goes through this. They go to the reactor from where it's an exothermic reaction. So I have to cool the reactor. I use a BFW stands for boiler feed water. You know it must be demineralized. Demineralized water goes through a heat exchanger for removing the heat from the reaction, and steam is formed. And cooled products, they come to again a heat exchanger from where they go to a separator. Then from the separator, you have what you call the gas and the liquid coming, and the liquid goes to a distillation column. The gaseous products, they go to an absorber, right? And from this absorber, again, separation is done. So you can see the recycle comes out here, and to prevent the accumulation of inerts, a small quantity of the recycle is purged out. You know the reason for purging, right? And then in this column, I do my separation. Column means distillation column, right? So my product is now got vinyl acetate monomer product is got, and I get two. That is the top and bottom, right? So sorry, column, and then go to a decanter, and from the decanter, the certain liquid, you get my what is that? Aqueous product, right? So this is the vinyl acetate monomer. Then come C3 compounds. C3 compounds, they include isopropanol, acetone, cumene, acrylonitrile, isoprene. Right? 1, 2, 3, 4, 5. Isopropanol. CH3, CHO, HCH3. CH3, CH, OH, CH3. Right? There may be many uses of isopropanol, industrial as well as common uses. It finds use in pharmaceutical application because of low toxicity of any residues. Isopropanol is also used as a chemical intermediate in some industrial processes. It is used as a gasoline additive also. Because branch chain hydrocarbons, they increase the octane number. Isopropanol, a small quantity is added to the gasoline. How it is manufactured? Sulfation. Remember, when we started the course, we had some unit processes in which sulfation, adding sulfur into the system, was one predominant one. Now it comes into action now. For isopropanol manufacture, I have CH3, CH2. What is this? Propylene. Propylene with sulfuric acid, I form isopropyl acid sulfate. Isopropyl acid sulfate. Then on hydrolysis, isopropyl sulfate with water. Hydrolysis means reaction in the presence of water. So this forms isopropanol, and the sulfuric acid is regenerated. Thus, sulfuric acid is regenerated, and the side reaction, you have to have headache, otherwise no fun. Isopropyl, diisopropyl sulfate, right, with the water form diisopropyl ether and sulfuric acid. Therefore, the primary reaction is a gas-liquid reaction in which propylene is absorbed into a tray tower fed with sulfuric acid. Operating conditions are room temperature, but 20 to 25 atmosphere pressure, right? And reaction is highly exothermic. Reaction is highly exothermic. So as you read the reaction, you should have a mental picture. Yes, we need a place to add sulfuric acid, then hydrolysis must be done, and then the separated sulfuric acid must be reused, and then product may contain unconverted propylene, and we'll have to separate and recycle the propylene back. So these all should come into your mind automatically for drawing the flow sheet. Okay, so remember, The refinery, if you go to the steam cracking, we usually get a gas which may both have C2 and C3. Right? Doesn't matter. See, so C2, C3 I feed in, right? And it is the pressure. What is it? 20 to 25 atmospheres, right? So it's compressed, put into the reactor, and sulfuric acid is added here, and some light ends come out, and then the product goes into a hydrolyzer stripper where hydrolysis is done. That is this plus H2O, right? So some dilute sulfuric acid is formed, right? And this is concentrated and then recycled, right? Then from here, we give a caustic wash. Why caustic wash? See, when we have used sulfuric acid, there may be some trace quantity of sulfuric acid present in the mixture of product. So a caustic wash will remove the sulfuric acid that is left over, which has not got removed. So caustic wash, this is a normal thing. Whenever you see sulfuric acid case uses, there will be one caustic wash, Remember, in the refinery also, we had done a caustic wash, right? So then it goes to, from the top, it goes to a condenser, and the top products are heated, and unconverted raw material is recycled back, right? And then what happens? From here in this condenser, I get liquid, one gaseous product and liquid product. The liquid product has alcohol and ether, right? It goes to a column where isopropyl ether. Remember, there is a side reaction forming isopropyl ether. Yes, side reaction, isopropyl ether. This has to be separated, and then it goes to another column for purifying, right? So two column, then remember isopropanol water. Isopropanol water is a azeotrope. Something very interesting. You'll be studying about azeotropes in the mass transfer course, right? Azeotrope or constant boiling mixtures. What do you mean? See, normally when the boiling points are different, so when I heat, the vapor liquid composition, the split of the component in the vapor and liquid phase will be different. That is my basis for separation distillation. But in case of constant boiling, I'll get the same composition in the vapor and liquid. Then that's called azeotrope, right? So water and isopropanol form an azeotrope. So to remove it, I must do a special azeotropic distillation to get my product isopropanol. Okay, if I am not interested in what do you call pure isopropanol, the azeotrope can be used for anything, then I don't need this column at all, right? So this must be kept in mind. So unless high purity isopropanol is required, I don't need to do the azeotropic distillation. So either pure propylene, I can use pure propylene, or a mixture of C2, C3 component can be fed to the reactor. You have the option. But there will be difference if you use pure propylene or a mixture, right? First try to understand what will be the implication. We'll come to it. Okay. Then the hydrocarbon feed is compressed and fed to the reactor. This is what we have discussed in the flow sheet, right? And sulfuric acid is added, yes, and the reaction, these are trays, right? Tray column, right? The reaction is exothermic, and refrigerated brine is used to control the temperature in the absorber. See, the reaction typically is at room temperature, right? So to maintain the room temperature, I use, what do you call refrigerated brine, so that the temperature is maintained. And otherwise, jacketed arrangement will be preferred for tray absorption column to circulate the refrigerated brine in the cooling jacket. Right. After reaction, the unreacted material will leave the unit as a gas stream. The sulfonated product rich stream is then sent to the hydrolyzer come stripper, right, where it is isopropanol is produced and is vaporized due to existing stripper temperatures. And the hydrolyzer is fed with water to facilitate the conversion of sulfonate product. Right. So we are adding water. The isopropanol rich vapor then enter a caustic wash to remove any sulfuric acid impurities. Then the isopropanol vapors enter into a partial condenser. That's what we have seen here, partial condenser, right? And to separate the unreacted propylene from alcohol ether mixture. Propylene is separated and alcohol plus ether. Ether is the side unwanted product, right? The separated propylene gas is again subjected to water wash to remove impurities. That is, this gas is mainly propylene, is given a water wash and then compressed and put back to the reactor. The alcohol and ether enter into a ether column, right? That is here to separate the side product isopropyl ether and then goes for the next last stage, right? The bottom product consisting of isopropyl alcohol and water. So the bottom product, where is this? Yeah? Is isopropyl alcohol and water, right? Yes. This goes for drying, and from drying it goes to the azeotropic column. Right. The azeotrope is sent to an azeotropic distillation column that uses isopropyl ether as azeotropic agent. See, remember azeotropic distillation, I will have to break the azeotrope by bringing another material. In this case, that is isopropyl ether. Right, isopropyl ether is added. To obtain 99% isopropanol as a bottom product. Top product is a mixture of isopropyl ether and water. The top product is a low boiling azeotrope. This stream, upon gravity settling, will produce the isopropyl ether as the top product, which is sent as a reflux stream to the azeotropic column. Bottom product is a mixture of isopropanol and water. It's recycled back to the isopropyl alcohol column along with the bottom product. Right. That is this is the put back to this column. Okay. So you see, in the case of isopropanol, right? We use one place we saw refrigerated brine because the room temperature has to be maintained 25 to 30 degrees. Then we have seen that the isopropyl ether is recycled back to the sulfonation reactor. Isopropyl ether is recycled back to the sulfonation reactor, right, to suppress the side reaction, right? So the way of suppressing the side reaction. That is why it is recycled back. Then comes acetone. Acetone is there in the lab always, right? One bottle in every shelf will be acetone. It is manufactured from isopropanol. The reactions are dehydrogenation of isopropanol. Just read the steps, then the flow sheet will be clear. Dehydrogenation of isopropanol. Isopropanol becomes acetone and hydrogen, that is dehydrogenation. So this is explained here. Isopropanol on dehydrogenation forms acetone and hydrogen is liberated. Pressure is 3 to 4, temperature 400 to 500 degrees centigrade, copper catalyst and porous carrier, vapor phase reaction. Right. So isopropanol, right? So you have the storage of isopropanol. Isopropanol is heated, right, and then compressed, and then go to the reactor where the dehydrogenation is taking place. The catalyst reaction, and from here it goes to a water scrubber, right? From there, it goes to the acetone column, from where the acetone product is removed, and the bottom they go to an isopropanol column, where the unreacted isopropanol is collected and put back to the reaction. Okay, so this is a vapor phase process. First, the isopropanol is heated using steam to vaporize the same. Remember, isopropanol steam is used to vaporize. Isopropanol is compressed to the desired pressure 4 to 5. This is a compressor. This is a heat exchanger using steam. The isopropanol has been heated and then compressed and then put into the reactor. Okay. The tube is packed with porous copper catalyst that we have already mentioned. Copper catalyst, right? And the reactor is operated at 400 to 500 degree using flue gas for heating. So we have to supply the reactor temperature 400 to 500. Some flue gases may be used. The flue gas is passed on the shell side of the shell and tube reactor, right? And after reaction, the gases are condensed using cooling water. This is a sequence we have seen. The condensed isopropanol and acetone are sent for fractionation. Fractionation means separating into different fractions. The acetone isopropanol, so acetone isopropanol mixture, right? This gear goes for this acetone column, remove the acetone, then the isopropanol is separated again here. Uses of acetone. Acetone is used as a polar aprotic solvent in a variety of organic reactions. One important property for which it is used as a laboratory solvent is because it does not form an azeotrope with water. Wow. So acetone does not form an azeotrope with water. Acetone is also used in various medical and cosmetic applications. It forms an important component in food additives and food packaging. Okay, so coming to the acetone, a few interesting things. Do we require pure isopropanol? Remember, the raw material is isopropanol, right? Do we require pure isopropanol or isopropanol with water chalega? Remember, isopropanol with water chalega. Right. If isopropanol with water chalega, then I don't have to use this azeotropic column in my acetone, because the product I get is isopropanol with water. Unless I want pure isopropanol, I don't need this azeotropic column. Right. So if you have an acetone plant adjacent, if you have a isopropanol plant adjacent to the acetone plant, then the isopropanol plant need not have this azeotropic column, because this input of isopropanol with water azeotrope can be used for the acetone making. Okay, that is one aspect. So I can use isopropanol with water also. Then what else? Why are we using high pressure? Remember, this is a dehydrogenation reaction. Normally, dehydrogenation means reduction. 1 mole of isopropanol forms 1 mole of acetone plus 1 mole of hydrogen. Increase in number of moles. And it is a gas phase reaction. So in such a case, you know that low pressure would favor. But still I am using 3 to 4, not lower pressure. Why? The reason being that there must be a special reason. The reason is that by using the pressure is not a very critical thing in this process, and by using a high pressure, I use a smaller reactor, right? So I am using higher pressure even though low pressure is favored, because of the reason my reactor size will be smaller in case I use a high pressure. Of course, as per Lee-Chatter's principle, low pressure favors this reaction because of increase in number of moles, right? And why I am using this recycle isopropanol? Remember, this the recycle isopropanol. I am again bringing it to compression. Why can't I? I'm heating and compressing. Why I need to do it? See, the reason being, this is at 4 to 5 atmosphere, but subsequently, right, the what is that? These these stages operate at lower pressure because of pressure drop. In fact, the last column is almost at atmospheric pressure, but the catalytic reaction will take place at 3 to 4. So my product must be heated and compressed and then put. So the recycle cannot be put directly into the reactor. It has to undergo heating and compression. Because if all this had been operated at high pressure, then there is no pressure drop. But that's not the case. But because the what do you call the pressure drop happens, which has to be compensated. Then comes the next important product, cumene. Cumene is isopropyl benzene. Wow. C6H5, C6H6 is benzene. So in benzene, one hydrogen is replaced by isopropyl, right? So CH3 twice, right? So to the benzene ring, you have CH, and the CH has got a CH3 and CH3, right? That is of the four valency of carbon is satisfied. It is an organic compound that is based on aromatic hydrocarbon with an aliphatic substitution. Benzene is aromatic, isopropane is aliphatic, aliphatic substitution in an aromatic compound. That is special, cumene. The constituent of crude oil. Crude oil has some quantity of cumene and also in the refined fuel. It is a flammable, colorless liquid that has a boiling point of 152 degrees C. Main reaction, benzene plus propylene forms cumene. Wow, straight. But there is a headache. Benzene plus propylene may also form polyisopropyl benzene. So, what is the catalyst? Phosphoric acid, impregnated catalyst on a porous carrier. Operating conditions are 25 atmospheric pressure and 250 degree centigrade. Okay, the simple flow sheet, let's have a look at it. Benzene, propylene, propane. So, see, remember, why I am writing propane? See, when you see the cracking column, propylene and propane come together. And if I use a C3 splitter, then I will split into propylene and propane. But if I don't want to split, then I may bring propylene and propane without splitting directly into my cumene manufacture. So propylene propane mixture with benzene gets compressed because the pressure is 25 atmospheres. They must be compressed and heated. Right. Heating is done by the bottom, the reaction. Remember, I think it is the exothermic, right? And so the heat must be taken away. The raw material must be heated. The product is cooled. The incoming feed is heated. It is put into the reactor, and I am now using this, for controlling my reactor temperature different by injecting water or steam. Okay, then my products get cooled by heating the incoming raw material and then goes to three column: depropanizer and benzene column and then cumene column. So they are arranged based on their boiling point sequence. So you have your depropanizer where first propane which may be there is removed, and then the next stage benzene column removes the what is that benzene column. Where is it? Yes. This goes to the cumene. So the cumene product is removed and some polyalkyl benzene is got, and the benzene is recycled back into the reactor, right? And here the cumene comes on top, cumene and polyalkyl benzene, because polyisopropyl benzene side reaction. So this comes as the bottom product and our desired product is on top. Right. As a thumb rule, always the desired product is preferred as the top product. This is one of the heuristics that we have seen in the process synthesis. Okay, so the same explanation is given here. What we have just now talked is mentioned here. You can read through it. Right. Now, we have to settle a few things. What is that? Which should be the excess reactant and limiting reactant? Right. Now, let's see, what is this says. Propylene is the limiting reactant. Presumably, all propylene undergoes conversion. Right. Propylene is the limiting reactant. Propylene is the limiting reactant. Now let's try to browse upon this. See, pure propylene, now let's have a few queries. If instead of propylene propane mixture, if I use only propylene, then what is the implication? If I use only propylene, then I don't have a depropanizer at all. This column is redundant. If I am using propylene, but I need to do something else. See, the propane acts as an inert and takes away some heat. But if my feed is having only propylene, then I must do some heat protection for my reactor, because propane was doing a job. It doesn't take part in the reaction. It is inert, right? So benzene and propane, they don't react at all. So propane was doing a job of hanging around and cooling the place. But if propane is not there, then additional cooling must be done. So I'll have to provide a cooling jacket in the absence of propane. And no propane, I don't need to use depropanizer also. Right? And of course, this propane also prevents this side reaction. Right? Propane will quench, or what do you call, this polymerization of cumene, right? And also, what is that? I use excess benzene, right, to prevent the polymerization, right? Excess benzene. Propylene is a limiting reactant, and benzene will be the excess reactant. Benzene will be excess to ensure that the product formed is cumene and the side reactions are avoided. Propane does not react but is a diluent or inert in the system. In that way, it controls the reaction temperature. So remember, propane had nothing. It came and got recycled back, but propane acts as an inert here, right? And controls the reaction temperature. And if there is no propane in your feed, propylene, then you need to provide a additional cooling jacket. Okay. So that is about the cumene. The remaining steps are already given in the slides. Propane does not react. The reactor unit must be maintained at 250. The product vapors are cooled using the heat integrated exchanger. The vapors pass to a depropanizer. This is what we said, right? And then the next stage, propylene is the limiting reactant, and presumably all propylene undergoes conversion. And we have seen that propane does the job of controlling the reaction temperature. It is inert and acts as a diluent, right? And the reactor units are maintained at 250 degrees. Then here, where is this? Yes. Here we separate the benzene column, right? And in the benzene column, the benzene comes on top, which is recycled back, and the bottom product goes to the final column where cumene and the other side products are removed. Then comes the next one, the last, I think, in the sequence, acrylonitrile, ACN. Short form is a very important chemical, CH2CHCl, the colorless volatile liquid, and commercial samples can be yellow due to impurities. Otherwise, it is pure form, colorless volatile. It has a pungent odor of garlic, onions. My goodness. In terms of its molecular structure, it consists of a vinyl group linked to a nitrile group that makes it special. Right. See, remember the heteroatoms bring special properties. Right. So bringing in a sulfur, right, bringing in nitrogen, they change the properties of the hydrocarbon. Right. That is our strategy in making the chemicals. The dominant route for manufacture of ACN, the one-step propylene ammoxidation process, replacing the original acetylene-based technology everywhere. Once upon a time, acetylene was there to for many chemicals, but now it has got phased out. Propylene, ammonia, and air are reacted in a fluidized bed reactor to produce acrylonitrile with the side product acetonitrile and hydrogen cyanide as byproduct. The original catalyst consisted of bismuth, phosphomolybdate, and silica, but recent catalyst developments have improved yields and can boast capacity of existing plants by 20%. The domination of licensed technology by BP Chemicals, British Petroleum, Sohayo, name, big name. In fact, when you say acrylonitrile, the name Sohayo comes because it is a company with a specially developed process for making acrylonitrile. And BP Chemicals ended this Sohayo domination in 1995 when Solutia Monsanto licensed the technology to Tae Hwang in South Korea. Now the Sohayo process is owned not by Monsanto BP Chemicals, but it is by the Tae Hwang in South Korea. New technology based on propane ammoxidation is being developed by a number of producers, which claims about 30% production cost advantage compared to the propylene route. Right. So the people are trying to replace propylene by propane, but right now propylene is the dominant one. Remember, propylene, CH3CH double bond CH2 with ammonia and oxygen form acrylonitrile and water. In the Sohayo process, propylene, ammonia, and air are passed through a fluidized bed, air, not pure oxygen. Right? That makes it cheap. Right? Pure oxygen means cryogenic separation and headache. Right? 400 to 500 degree, 50 to 200 kilopascal. Right? KPA gauge. KPA G stands for KPA gauge. Right? Gauge pressure. The reactant pass through the reactor only one through before being cooled in aqueous sulfuric acid. The excess of propylene, carbon monoxide, carbon dioxide that do not dissolve is vented to the atmosphere or incinerated, and the aqueous solution contains acrylonitrile, some unwanted acetonitrile, HCN, and ammonium sulfate. They are produced from excess ammonia, right? And recovery of column removes the water and acrylonitrile and acetonitrile by distillation. So this is the flow sheet of the Sohayo process. I have my air ammonia propylene, and it's an exothermic reaction. The boiler feed water, BFW, it becomes steam, high pressure steam. Remember, the pressure used in the process is 50 to 200. So, by cooling, high pressure steam is produced. The fluidized bed reactor, then it goes to an absorber with water, right, and then goes to a series of separation columns, right. The crude acrylonitrile is got, which goes, into the next separation, and here again the bottom product you get crude acetonitrile, which is also maybe used, right? But the main product acrylonitrile, it goes to two separation column where product acrylonitrile and heavy impurities are separated. Okay. Then minute more, We have the last of the chemicals, that is isoprene. Um, Okay, I think I'll take up isoprene in the next lecture. Isoprene, the very important C3 chemical, and it is what is the synthetic equivalent of natural rubber, right? Isoprene, the unsaturated hydrocarbon. We'll pick this up in the next lecture, and so we'll end today. Thank you all. Thank you.
Thank
Okay,
you,
thank
sir.
you all. And the PPT for today's lecture has already been uploaded. You are welcome to go through it. And so, thank you.